Well, hello and welcome YouTube. Mr. Robbins back here with yet another brand new exciting video, all math basic course. And as always, it is an honor and a privilege to be serving you today, as it is every day, here in my virtual classroom. Step on inside as we jump into section 5.2 in the Big Ideas Math Integrated Math 2 textbook on independent and dependent events. I'm going to pretty much jump right into it here. If you want to follow along, go to the description section down below and you can download this PDF I'll be navigating through. I'll start with the lecture portion, then I'll go to the problem set, and you can find those timestamps for when each part occurs. So from the lecture, and again, problem set maybe 20 minutes after, who knows what it's going to be. We came off section 5.1 on sample space and probability. This whole chapter's on probability, big part of statistics. In that last chapter, we did a lot of slowdown. We had a lot of spelling some things out in a big old way. I'm hoping this one's a little more formula based off what we learned. And then it'll be a little quicker with that. 30 problems in the set. Let's go ahead and look at the lecture portion to begin with. What we're going to learn how to determine whether events are independent or possibly dependent, and find probabilities of independent and dependent events. They are different based on whether it's one or the other. And then find conditional probabilities as well, which I'll talk about when we hit that portion in the lecture. As you can tell, those are the three terms in our core vocabulary. And then the previous ones from that section called sample space and probability are the previous terms there. So let's go and get started. Let's determine whether events are independent. Two events are independent events when the occurrence of one event does not affect the occurrence of the other event. Events are things like I flipped a coin, that's an event. I flip another coin, that's a second event within the thing. Or I draw a card and I draw another card. So we'll see which specific examples will make these things happen. You need to understand what will make them happen as well, but there's also a formulaic version of understanding it. So they do have a formula with that. Two events A and B are independent if and only if the probability both events occur is the product of the probabilities of the events. So the probability of A and B occurring is the same as the probability of A times probability of B. And hopefully it will make sense why that is, not just when it's independent, but also what would make them dependent as well. And we're going to be hitting both of those at the same time. So that is probability of A occurring times probability of B occurring. Get used to doing the multiplication of things when we're talking about an AND case, and being multiplication. So let's take a look at a first example, determining whether they're independent. A student taking a quiz randomly guesses the answers to 4 true-false questions. Use a sample space to determine whether guessing question 1 correctly and guessing question 2 correctly are independent events. That means, and what they're stating here is, does the probability of answering question 2 correctly depend on whether the probability of getting question 1 correct, whether or not you got question 1 correct? Does it depend on that? I mean, I want you to think that for yourself to begin with. But let's go ahead and take a look. Using the sample space in example 2 on page 281, I have no idea where that thing is. Oh, I remember that we did that though. If you recall, there was the whole 4 incorrect versus 1 correct, this kind of spelling thing. You'd have to check out section 5.1 on that. But it's kind of that same layout of a question, but now that we're talking about the independent-dependent thing here. Basically, the probability of getting something correct on question 1 was 8 out of 16. Basically, there were 8 different ways in arrangements that question 1 could have been answered correctly. I'm not looking at the sample space. I apologize. I don't have it set up here. But that's a 1 out of 2 probability. And same with question 2. And I think that you'd agree that that would make sense when it comes to a true-false thing. But as far as question 1 goes, and question 2, there it is. Now, what is the probability of getting question 1 and question 2 correct? There were only 4 out of 16 ways to do that. Let me at least write those 4 out, right? We can either get both questions 1 and 2 correct. We can either get both questions 1 and 2 correct and 3 and 4 incorrect. Or you can get these correct and 3 correct and 4 incorrect. These correct and 3 incorrect and 4 correct, or all 4 correct like that. These are the 4 ways out of the 16 different ways that you can answer questions here that would happen. So 4 out of 16 is 1/4. Now 1/2 times 1/2 is also 1/4, therefore the events are independent. And that makes sense. The probability of getting question 2 correct should not depend on whether or not you got problem 1 correct, especially if you didn't know whether or not you got problem 1 correct, but you're randomly guessing anyway, and that's not going to affect the outcome of getting question 2 correct. It does make sense that they're independent in that case. So let's look at the second example. We have a group of 4 students, includes 1 boy and 3 girls. The teacher randomly selects one of the students to be the speaker and a different student to be the recorder. So it's completely random. Use a sample space to determine whether randomly selecting a girl first and randomly selecting a girl second are independent events. So I want you to think about this one as well, logically, before we actually get into the math of this. And I want to see how they're spelling this out, because I have to do this probably in the problems because they're based off the examples. Let's just think about it to begin with. I randomly select a student first, and then I randomly select a student second. But if I randomly select a student first, whether boy or girl, it pulls that person out of the pool of who I can select second. It says a different student to be the recorder after you select a student to be the speaker. So if I select a boy to be the speaker, all that's left to select next are girls. So the probability of selecting a girl, suddenly it became 100%. Now, they're different girls, but suddenly it became 100% because I selected the boy first. Whereas if I selected a girl first, all that's left is one boy and two girls. And the probability of selecting a girl has now changed because there's one less person taken out, and that person was a girl. This should have to be a dependent event. But let's see how they mathematically demonstrate that as well. Does the probability of A and B equal probability of A times probability of B? So first of all, let's just see the probability of selecting a girl first. Now, they spelled out the sample space here, and they show either girl 1, which they didn't do this last time, showing the subscripts. But you can select girl 1 and a boy, or boy and girl 1, girl 2 and a boy and girl 2, etc., or different sets of girls, girl 1 and 2, or 2 and 1, 1 and 3, 3, 1, 2, 3, 3, 2. So these are all the 12 different ways that you can select the 4 students in this overall set. Now, the number of girls overall, there's 1 girl overall in the first set of 6, and there are 2 girls overall in the second set of 6. Probability of selecting a girl first, you can see there are 9 different ways that a girl can be selected first out of the 12. That's 3/4. There's a 3/4 chance that a girl is selected first. I mean, that makes sense overall. And there's also a 3/4 chance that a girl is selected second. This is not assuming the girl is selected first. This is just in a general case. Or at least when you also take a look at the sample space there, there's a 3/4 chance that a girl is selected second. But when you multiply 3/4 by 3/4, 3/4 times 3/4 is 9/16. 9/16 doesn't reduce, but the probability of selecting a girl first and selecting a girl second, you can see here that would be, they say 6/12. Let's see. Girl first and girl second, that's the bottom set. 2 girls, that's 6 out of 12, which is 1/2. So using the sample space shows that 9/16 is not the same as 1/2. 9/16 is not the same as 1/2, so these events are not independent. You might not fully understand the math portion of it unless you work out spelling out the sample space, which it looks like we still have to do those. But if we understand the logic behind the dependency of the matter of the fact that if I selected a boy first, it changed the probability of selecting a girl second, or if I selected a girl first, it changed the probability of selecting a girl second, that set itself already shows it's not independent, it's dependent. And they haven't defined dependence yet for us. We'll see if they do that here in a second, because it's a vocab word. Okay, let's move on. Finding probabilities of events. In example 1, it makes sense that the events are independent. Oh, this is what I was saying. It makes sense the events are independent because the second guess should not be affected by a first guess, right? No, we already said that. In example 2, this is what I said, the selection of the second person depends on the selection of the first because the same person cannot be selected twice. So once you selected a person, they're not replaced. That's a phrase that they're going to say a lot, with replacement or without replacement. The person's not replaced, they're not put back in. There are less people and less girls or boys. These events are dependent. Here you go. 2 events are dependent events when the occurrence of one event does affect the occurrence of the other event. I feel like they should have defined those 2 together, but they'll probably have a different formula for you. The probability of that event B occurs given that event A has occurred is called the conditional probability of B given A, and is written as this: probability of B given A. Let's put it this way. Find, because they're probably not going to do location ones. Find the probability that a randomly selected voter lives in Los Angeles, okay, in the nation, okay, that a randomly selected person is a voter from Los Angeles. Okay, it's whatever, 1.1%. Find the probability a randomly selected person is a voter in Los Angeles given that they live in California. Now you just narrowed that outcome of what's there. You narrowed the focus down to that. It's going to be a lot bigger. Maybe it's 9% or something now. But anyway, so just that idea that given that something occurs, Completely changes the way that you narrow your focus on what you're looking at. So let's see what they mean here. Probability of dependent events. If two events A and B are dependent, then the probability both events occur is the product of the probability of the first event and the conditional probability of the second event given the first event. So they write probability of A and B is not probability of A times probability of E, but probability of B given that A occurred first, or that A does occur, that A is what we're looking at. So that girl and boy one, actually they're showing it right here, probability of girl first and girl second is probability of girl first times probability of girl second given girl first. What the heck does that mean? Let's think of it in just the case that we're talking about, like logically, before we look at the sample space here. Logically, if I select a girl first, right, there are 3 girls and there's 1 boy. If I select a girl first in that first position, it took out a girl from this set and it took out a person from this set. So before, initially, there was a 3/4 chance that a girl was selected to begin with. And then times, we do and, what's the probability a girl selected next? Suddenly, there are 3 people left and only 2 girls. So suddenly, when a girl is selected in the second set there, in the second set, that is 2/3. 2/3. Now notice here, they're building off this sample space to begin with. There was 9/12 to begin with, but then once a girl was selected, now we're only looking at the sets where a girl was selected first, and then what's the probability a girl selected after that? It's 6 out of the 9, because we're not looking at the set where a boy is selected first. So 6 out of 9, that is 3/4 times 2/3. So there is a way to do this logically. There's a way to do it through sample space as well. They're both logical. One's more practical than the other. And that's where you get the 1/2 case instead of the 9/16 that you saw before. Okay. So finding the probability of independent events. Okay, I thought they said dependent, but let's look at that. As part of a board game, you need to spin the spinner, which is divided into equal parts, so 1 through 8. Find the probability you get a 5 on your first spin and a number greater than 3 on your second spin. Okay, first of all, well, I think they'll say it, but even though you land on some spot like this 3, sure, the force that I put on the spin is going to land it a certain number of revolutions over, but we're going to call it independent in the sense that the landing on a spot is random, and the amount of force you put on it is random. So I could hit 3, and I could hit 3 and again, and a third time and stuff. If I land on 3, that doesn't change the probability that I land on 3 again. Or if I, like flipping heads, I can flip heads over and over. It's not going to mean, surely that means there are going to be a lot more tails along the way. They're random. So these events are independent. They say it right here. The outcome of your second spin is not affected by the outcome of your first spin. So there are 2 probabilities in play here because there are 2 different events. Event A is landing on a 5 on the first spin. That's a 1/8 chance because there are 8 things total, all of equal likelihood. 5 is one of the 8 targets. So you have a 1/8 probability of landing on 5. And then probability that you have greater than 3 is 5/8. So whenever you do probabilities, you multiply for 2 events, one and the other, you multiply those 2 probabilities, and because they're independent, we just multiply them straight up. 1/8 times 5/8 is 5/64, or 0.078, 7.8%. It's just multiplying one and then the other. And we do the multiplication for reasons, I don't think, because I'm already 13 minutes in, I'm not going to get too deep into that. But let's just imagine flipping a coin, 50% chance, 1/2 that you land on heads, and 1/2 again that you land on heads. What's the probability you land on heads twice? Well, that's half of a half, right? 1/2 times 1/2, because you have to dig deeper into that. Anyway. Okay, here we go. Second one on dependent events. A bag contains 20 $1 bills and 5 $100 bills. You randomly draw a bill from the bag, set it aside, then randomly draw another bill from the bag. Find the probability both events A and B will occur. First bill is $100, second bill is $100. So once we draw, remember, we first look at what's the probability that you draw a $100 bill. There are 5 $100 bills out of 20 bills total. 5 out of 25 is 1/5. Looks like they reduced it right here. So there's the 1/5 because there are 5 of them. Now we're going to multiply that then by the probability of getting a second bill that's 100. But the second one is probability that a $100 bill is drawn given that you drew a $100 bill the first time. And when you draw a $100 bill the first time, notice that we remove not only a 100 from the set, but an entire bill from the set. So there are not 25 bills in the set anymore. There are 24 of them. And there aren't 5 $100 bills left, there are 4 of them. Because remember, we're assuming a $100 bill. We're not assuming. This is given that a $100 bill is drawn the first time. So we do 5 out of 25 times 4 out of 24, or 1/5 times 1/6, which is 1/30, or about 3.3%. So one outcome affected the other outcome because we set it aside. That was without replacement. Another way of saying that. They're going to say that sometimes. Okay, comparing independent and dependent events. Now let's select 3 cards from a standard deck of 52 cards. What's the probability all 3 cards are hearts when you replace each card? That's the phrase with replacement. And if you do not replace each card. See, if I draw a heart and then put it back in the deck and shuffle it, whatever, and then that heart is back in the deck, which means there are 52 cards. There are, and you have to know this, there are not 4 hearts. I was thinking of queens. There are 13 hearts total, because it's a quarter of all of the cards. That heart is there, and like that. So it's equally likely once again that you draw a heart again. So that 13 out of 52 is occurring for each event because you put that card back in, so it has equal likelihood as it did before. 1/4 times 1/4 times 1/4 is 1 out of 64, about 1.6%. But what if you don't replace that heart card? If you don't replace the heart card, notice you had 13 hearts to begin with. You had a 1/4 chance, 13 out of 52. But then that heart is gone, and there are 12 left. And there are only 51 cards left. Now there's a lesser chance you draw a heart because there are 13 of each other suit, and there are only 12 hearts. But let's say we draw another heart, given probability of B given A. Now there are 11 hearts left and only 50 cards left. You're reducing your probability. This is a smaller probability than that is, and then that is. Much smaller? Not necessarily, but smaller, yes. So ultimately, when you multiply those, if things reduce, right, whatever, you get about 1.3%. So 1.3 is less than 1.6. So you're and you're actually comparing as far as how many times more likely. You won't just say 0.3% more likely. You're actually checking out what factor it is. So dividing this number by this number, or they show them as exact fractions, you're 1.2 times more likely to select 3 hearts when you replace each card. And I think that's important to say, right? 5% versus 10% isn't 5% more likely. You can say that, or 10% versus 5%, but it's twice as likely. You're twice as likely to do something if you have 10% chances versus 5% chances. Okay. Using a table, this is a long lecture bit. Using a table to find conditional probabilities. Here we go. We have a table of pass, fail, defective, non-defective. It's called a two-way table. A quality control inspector checks for defective parts. The table shows the results of the inspector's work. Find the probability a defective part passes and the probability a non-defective part fails. Notice that they say the phrases defective part and non-defective part. They don't just say inspection or any part, I should say. So this is called a conditional probability. Given that we're only looking at defective parts, what's the probability that it passes? That means that even though there are 39 total defective parts and 461 total non-defective parts, and 39 plus 461 is 500. Even though there are 500 total parts we're talking about, when we're looking at part A, probability a defective part passes, we're only looking at the 39 here. Given that we're looking at a defective part, what's the probability that it passes? So we're going to do 3 out of 39. 3 out of 39, that's 7.7%. We don't care about the non-defective ones. They didn't ask us that. If I was in my class and I said, what's the probability that girls today brush their teeth after lunch? I don't know, whatever. I don't care about the guys in the class. I only care about the girls in the class as far as that question goes. The guys are irrelevant to the probability. Part B, the probability a non-defective part fails. We're only looking at the non-defective parts, the 461 that are here. So only 11 fail out of the 461. Now, what if I said that any part fails? That would be out of the 500, that would be 47 of them. But they didn't ask that. These are conditional ones where we do these ones. 2.4% in that one, we do 11 out of 461. So you can rewrite the formula for the probability of dependent events to write a rule for finding conditional probabilities. Given that we saw that in a dependent event, you multiply probability of A times the probability of B, given that A occurs, you can also find a given probability by dividing both sides by probability of A, for example, as probability of A and B occurring out of probability of A occurring. This is like probability of being defective and failing out of the probability of being defective to begin with. Things like that. Because we're only looking within the scope of just defective parts. Okay. Anyway, finding a conditional probability. Let's see those percentages at play. At a school, 60% of students buy a school lunch. Only 10% of students buy lunch and dessert. What's the probability a student who buys lunch also buys dessert? See, it's not just 10% because they're saying only among the students who buy lunch, not all of the students. Remember, if 60% of students buy lunch, 40% don't. But I don't care about that 40% within there because the 10% that occurs here is 10% of all students, not 10% of lunch buyers. 10% of all students buy both lunch and dessert, but if only 60% buy lunch, then you want to divide the 10% out of the 60%. See, there's a pie chart. There's a pie chart here where we have 60% of students that buy lunch and 40% of students who don't buy lunch. Within the 60% who buy lunch, there's a 10% of the overall that buy both, but 10% out of the 60 is what we're looking at. And 10% out of 60 is 1/6 or 16.7% about. So that's what we're looking at for conditional probabilities in that sense, and we'll make sure to practice those. Okay, quite another long lecture there, another big 21-minute one. Let's go ahead and take a look at the vocabulary and core concept check before we get into the other parts. Writing. Explain the difference between dependent events and independent events and give an example of each. Ooh, tall order. So as far as the dependent events occur when the probability of a second event is affected by the probability of, or by the first event that occurs. I know they say it better than I do, and I'm sure I could have said it better, but I didn't. Independent events do not depend on each other, are not altered by one event occurring, having occurred. Right? Flipping a coin, I land on heads. That doesn't change my probability of landing on heads or tails again after that. Now, well, they said give an example of each, so I kind of just said one for, so example, coin flips for that one. An example for here on independent, I want to try and do something different, not drawing a card one, because I don't think they did coin flips before. So a dependent event, let's do, where did randomly selected student, shoot, I want to do one we haven't done. I'll just say Wordle. Now, why does Wordle matter? Because me guessing a word, if you don't know what Wordle is, it's the guessing word game, the 5-letter word thing. Me guessing a word changes my probability of getting another word right later. Why am I more likely to get an answer correctly on the 6th try than I am on the first try? Because I've eliminated letters from occurring. I know which letters will go in place there. I know, or which ones exist in my word. That's a dependent set of events. My probability is increasing every single time I make another guess, given that I didn't get it right on another time. And that's how conditional probability works. That's actually a really good example for modern day and stuff. Complete the sentence. Number 2, the probability that event B will occur given that event A has occurred. Probability event B will occur is called, is the blank of B, hold on. The probability that event B will occur given the event A has occurred is the conditional probability. I was thinking it was a single word thing, but I was like, no, I have to say 2 things. So conditional probability. And is written as probability of B given A, that B given A looks like this, like that. So those are conditional probabilities there. Okay, guys, I'm going to go ahead and get started on the actual problem set itself. So this is numbers 3 through 30, I believe. So, yep, let's go ahead and get started on that one. Okay. Exercises 3 through 6, tell whether the events are independent or dependent. Explain your reasoning. So, A box of granola bars contains an assortment of flavors. You randomly choose a granola bar and eat it, then you randomly choose another bar. So if I ate that granola bar, then I can't randomly draw from it again, right? I can't eat it again, so it's gone from the set. So the probability of drawing a second kind of bar after that, it says you choose a coconut almond bar first and you choose a cranberry almond bar second. So they're kind of saying what's the probability that event B occurs given event A occurred? It's going to be a dependent event. It's going to be dependent because the outcome, the probability of event B occurring, or of choosing a cranberry almond bar depends on the fact that you chose a coconut almond bar first. Right? Because then it's one less coconut almond bar in the set. I can probably do that bigger. There we go. If I don't select that spacing first beforehand, then it doesn't space itself out right. The second time that I do this, it'll space itself out right. But that should be number 3 when it comes to that. Okay, number 4. You roll a 6-sided die. Oh, I have to move the thingy. You roll a 6-sided die and flip a coin. Event A, you get a 4 when rolling the die. Event B, you get tails when flipping the coin. Are these independent or dependent? Well, these are clearly independent. The fact that I got a 4 when rolling the die doesn't change the fact or the probability of landing on tails. So these events are independent because rolling a 4 does not affect the probability of, I do misspell probability, I guess, of landing on tails. You can see how the spacing was actually normal this time. Number 5. Your MP3 player. Do you guys know what an MP3 player is? I guess your phone these days. Your MP3 player contains hip-hop and rock songs. You randomly choose a song. Then you randomly choose another song without repeating the song choices. Because the song choices don't repeat, once that first hip-hop song was chosen, you're not going to choose it again. It won't be randomly chosen again. That's actually how shuffle works on things like iTunes or in cars for the most part. It says like you have tracks 1 through 12 and it starts on 6 and then it goes to 8 and then it goes to 1 and then it goes to 12. 6 won't pop up again in the shuffle, or 8 or 12, until you've completed all of them. So the probability of getting to track 3 is no longer 1/12. It reduces every time that 3 isn't hit, given that all these others are hit. So this is totally dependent. This is dependent because the probability of choosing a rock song has increased. I'll say specifically, it has increased. I probably should say it for the other one as well, after having chosen a hip-hop song first. Because it's not being replaced. Do they say replaced? What do they say? Without being repeated. It's not being repeated. Number 6. There are 22 novels of various genres on a shelf. You randomly choose a novel and put it back. Then you randomly choose another novel. The probability of choosing a mystery novel and then science fiction novel. Because you put it back, you have now provided the likelihood being the same as it was before. So this is independent because the probability of choosing a science fiction novel has not changed after choosing a mystery novel since you put it back. Once it's replaced, it becomes they become independent events. I have equal likelihood of choosing a mystery novel as I did before. Same with the science fiction novel. All right, let's go on to exercises 7 through 10. Determine whether the events are independent. You play a game that involves spinning a wheel. Each section of the wheel shown has the same area, so 1/4 each. Use a sample space to determine whether randomly spinning blue and then green are independent events. Well, I can tell you they'll be independent, so I got to think of the sample space thing. So blue and then green, for us also means as far as sample space goes, we're going to do 2 spins. So what are the different spin choices here? If we started with blue, I'll just write these this time. There's blue and blue, right? That's possible. It's not like blue goes away. There's blue, 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 yellow, blue, green, and blue, red. What if we start with yellow? There's yellow, blue. I'm going to keep repeating like this. Yellow, 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 green, and yellow, red. And then it keeps going. Let's go to green. Green, blue, green, yellow, green, 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 red, or red, blue, red, yellow, red, green, red, red. So there's a sample space of 16 different outcomes that can occur. What's the probability? It says use a sample space to determine whether these are independent events, spinning blue and then spinning green. So what's the probability of spinning blue in general? Probability of spinning blue should be 1/4. Now in this case we can support that by showing there's 4 out of 16 ways that you can spin blue first, or in this case spinning blue second, even 4 out of 16. But either way, it's a 4 out of 16 probability of spinning blue. 4 out of 16 or 1/4. Probability of spinning green is the same kind of thing. It's either the greens here to start with or the greens second to start with, to end with, but 4 out of 16 or 1/4. That's just off the sample space. Now, the probability of doing spinning blue first and then green second, as far as looking at this, that is right here. Blue first and then green second. It literally says and then green. It's not green and then blue. That's not one that counts there. So that's 1 out of 16. The question is the probability of blue and green equal to probability of blue times probability of green? 1/4 times 1/4 indeed equals 1/16. So yes, because the probability of one times the other equals the probability of both, these are indeed independent. And that sample space helped us for this problem because they didn't tell us what the probabilities were from the jump. And we can't assume probability of blue and green to be 1/16 because otherwise we would then know it is independent. We have to actually fill out that sample space and see that. All right, number 8. You have 1 red apple and 3 green apples in a bowl. You randomly select 1 apple to eat now and another apple for your lunch. Use a sample space to determine whether random. So based on this stuff, the conversation that we had, we should know that this should be dependent, not independent. But they do say use a sample space, so we will do that. Keep in mind that as we have here, and they used subscripts last time in the stuff. So what they say, red apple. There's 1 red apple and there are 3 green apples. 1, 2, and 3. Here's our set that we can choose from. Now let's see how we choose it. Notice that they say you select 1 apple to eat now, so I eat it, and when I eat it, it's gone. And so unlike the spinner thing, if I spin on blue and land on blue once, I can't land on blue again in the sense that, I could land on blue here, but I can't if I choose a red apple to start with. I can't get another red apple. I only have 1 of them. And then I can choose a green apple. So here are my options. I can do red now and green later, but it's any of those 3 green apples I could choose from. Then I could do the first green apple with the red, or the green apple with the first with the second one, or the first with the third one. And then the second one with the red apple, or second one with the first one, right? Or the second one with the third one. But I can't eat the second one twice, right? Or third green apple. 1 and G3, G2. So there are 12 different outcomes that you can have here. The probability, what did they say? A green apple first and a green apple second. Let's see what that is. So probability of green first, and I'll kind of just say that. Green first is what? Out of the 12, there are 9 different ways that a green apple can be selected first here. Even if red is selected second, that's 9 out of 12. And 9 out of 12 is 3/4. So the 3/4 probability that green selected first. Now, probability that green selected second is, let's look at the ones that are second. We can ignore those ones and we can look at these ones. That is 8, 9. That's also 9/12, which is 3/4. Now let's see the probability that you select green first and second as an overall. And then let's see if by multiplying these we get the same thing. So probability of, whoops, that is not a P. Probability of green first and second. Sorry, I'm just kind of saying it in that way. Green first and second is just this set right here. Notice we have to eliminate the ones that have red in it. None that have red, that's 6 out of 12. 6 out of 12, which is 1/2. The question is, does 3/4 times 3/4 equal 1/2? 3/4 times 3/4, does it? Well, 3/4 times 3/4 is 9/16. 9/16 does not reduce to 1/2. They are not equal. So these are not independent. Now we should know that. We should know that if I select a green apple first, that has reduced my probability of selecting a green apple second, because now there are 3 red out of 11 green apples. That has increased my probability of selecting a red. So that's the answer to number 8. Numbers 9 and 10, we still have to use a sample space, it looks like. So let's keep moving. Number 9. A student, and like I said, I want to kind of answer these first beforehand in terms of the dependent versus independent, but the sample space thing is helping show the formula. You might be wondering why that formula is important, because we will not always see things as a sample space. We will also see things as just straight up probability. So that's why we're practicing that. Number 9, a student is taking a multiple choice test where each question has 4 choices. The student randomly guesses the answers to the 5-question test. Uses sample space to determine whether guessing question 1 correctly and question 2 correctly are independent events. They should be independent, because answering question 1 correctly should not change the probability of answering question 2 correctly. So what are our options here? They said 5-question test, but they're really just talking about questions 1 and 2. So what are the different ways that we can do this? We can be both correct, or correct and incorrect, or incorrect, incorrect, or both incorrect, like that. So the probability of getting the first one correct in general, what did they say? Question 2 correct and question second correct? Second question correct. So correct first question is 2 out of 4. Notice that this one's has the first one correct there. So 2 out of 4, which is 1/2. And that makes sense. This is a true false. No, I'm sorry. Multiple choice. Oh, it's 4 choices. I'm sorry. So correct first is not 4. Let me think about that then. Each question has 4 choices. Student randomly guesses the answers to the 5-question test. Then this isn't about, let's see how I say this. This is where we would have different ways of getting things incorrect. Okay, I might want to type this one out, because this isn't just for 4 things. If you're incorrect, you'd be incorrect for the first option that's incorrect, or the second, or the third. Right? It's like an A, B, C, D. If A is the correct answer, B, C, and D are all incorrect. So if you randomly guess, you might guess A, which is correct, but you also might guess B and C and D. So this is our way of saying that. So I need to find a way to do this that's going to be quick. I don't know if it's going to at all. What I want to do here is the correct and incorrect that I just did before, but notice that there are going to be different ways you can get something incorrect. There's incorrect 1, or incorrect 2 or 3. This is going to be a larger sample space to actually do. So you can be correct on the first one, but get, oh geez, I don't know how to do a thing faster than this. So 1, 2, 3 like that. Okay. Or you can get, hold on, I'm going to kind of just do this several times here and see if this is going to actually work in a good way. I can get the first incorrect and the second incorrect. Oh boy, this is going to be well. Let's start with this as sample space. First, all 3 are both correct like that, right? Okay, yeah, that's what I have to do. If the first is correct, you can go like that. So boom, 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 boom. Or you can get the first incorrect and the second correct. This is going to be hard. Let me pause this for your sake and then get this spelled out. Okay, that actually didn't take too long once I just realized I could just copy and paste and replace like that. So here are the 16 different ways that the first 2 questions can occur. Either both correct or, you know, both incorrect, right? But there are different answers you can put for A, B, C, D, things like that. So there's 16 different outcomes for the first 2 questions on how they can come to be. But we say, what was it? Probability that they're both correct. So let's go back to that. Probability of first correct. What's probability you get the first correct? 4 out of 16, which makes more sense. There's the 1/4, right? So it's not true, false. It's multiple choice, 4 different options. It makes sense that it's going to be that. Probability of second correct on its own basis from the sample space that we're looking at. The second correct is going down this line right here. Hold on. Going down this line right here. And that's another 4 out of 16, or 1/4. Now, what's the probability you get both correct? The only one is that one in the top left corner, right? In the top left corner, we have just one possible option out of the 16. So both correct is correct and correct, 1 out of 16 like that. The question is 1/4 times 1/4 equal to 1/16? The answer is yes, 1/16 equals 1/16. So because of that, these are independent events, and we expected that. So independent. Sorry to begin with, I thought it was true, false. Because the other ones were previously. Okay. But we predicted independent there. Number 10. A vase contains 4 white roses and 1 red rose. You randomly select 2 roses to take home. Use a sample space to determine whether randomly selecting a white rose first and randomly selecting a white rose second are independent events. Well, they shouldn't be, because once you selected that white rose first, it has now diminished the number of roses available and white roses available. So we're expecting a dependent event. Now, when it comes to this thing here, I think it's going to be the exact same thing as what it was before. I have to get a lot of subscript stuff going. So there are 4 different white roses. There's white 1, 2, 3, and 4. I feel like in this case, I'm probably once again going to do I'm going to probably pause it and bring it back. And then there's a red rose. Let me just kind of get the idea. Whoa. Let me get the idea first going for you. No, I need it like that. There we go. So white 1, 2, no, 2, 3, and 4. So those are the different options, right? So I'll pause it, and then I'll get this thing spelled out with all the different options, and then I'll come back with you guys on that. All right, here we go. All right, so this is what I just put together here. Let me actually bold that. So there we go. So here's what I put together, the 16 different possible things. Now, even though there are 5 options here, this one is different from the previous one. You're saying, how come this is 16 and there were 4 options, and this is 16 and there are 5 options? Really, it's because of the dependency of how this thing works. Once I select a rose, it's gone from the pool. So in this last one, I could do correct and correct, right? It's not like, oh, you got the first answer correct, you can't get the second answer correct anymore. Or you selected A on this, you can't select A again. See here, if I select that first white rose is gone from this set. I can't do it again. So there's no white 1 that's available. It's white 1, white 2, or 1 and 3, or 1 and 4, or 1 in the red rose. So there's no repeat of that. So only 16 options, but we go back to the question at hand, which is what? Selecting a white rose first and randomly selecting a white rose second are independent events. Now, they shouldn't be, but let's see about the white rose first. And it doesn't matter which white rose, but we wanted to lay them out to make sure we knew which ones we're choosing and such. So white first. So white first should be, for us, whether we're looking at counting this out or whatever, should be 4 out of 5. There are 4 white roses out of 5 total roses. But let's see how we would look at it here. All the ones where you can do white rose first. Oh, you know what I don't have on here? Hold on. I am missing a set from here. You know what I'm missing? Red. But what I wanted to say wasn't that, okay, there are more than 12 anyway. That was 16. But there is a set that I'm missing. Hold on. I'm missing red. I was going to say probability looks like 100%, so something was totally missing. So red. Oh my gosh. I don't know how to kind of fix this when that happens. Red. See, this is why I paused, man. Red. And red, but not here. This should be a white 4. There we go. Okay, sorry about that. I was totally missing this set. I thought there were going to be less of these sample space questions as an overall. Maybe it's done after this number 10. But, okay, now, what do we have? We have this whole set, these 16 ones you can select a white rose first. That's 16 out of, there are 4 more after that, there are 20. And that is 4/5, which makes sense in the sense that there are 4 white roses and 1 red rose. But that overall combination set still shows up that way. Now, the probability of selecting a white rose second in general. They're not saying given that you select one first or anything like that, just the idea of selecting a second white rose. If you look at this set, ignore the ones that are red here, but look at every other one that's there. So there are 20 of them. You take away those 4, that's 16. So that's another 16 out of 20. Now 16 out of 20, once again, is 4/5. But the probability of white and white is, now we just got to find the ones that don't have red. So which ones don't have red? Just these sets right here. There are 12 of them out of the 20, I believe. 12, yeah, 13, 14, 15, 16, 17. Yep. So 12 out of 20. And 12 out of 20, divide those by 4, that reduces to 3/5. Now the question is, does 4/5 times 4/5 equal 3/5? Because if it does, then they're independent. If it doesn't, they are dependent. So that's 16/25 here, and here's 3/5. 16/25 does not reduce, so it's not the same as 3/5. It's very close. 3/5 is 15/25. But it's not the same, so therefore they are dependent or not independent. And we didn't expect them to be. Okay, that's number 10. Number 11, problem solving. You play a game that involves spinning the money wheel shown. You spin the wheel twice, find the probability you get more than 500 on your first spin, and you go bankrupt on your second spin. Now, with this question, notice that they did not ask about dependent or independent, but it matters. It matters because does getting the second one, is this probability of the second one dependent on the outcome of your first one? The answer here is no. When I spin that wheel, my probability of going bankrupt has not changed for my second spin. It's still the same. So, probability you get more than $500. We have to see which ones are more than 500. And I don't know if you can tell here what they are. I'll have to find a way to let me copy paste this onto the bigger set to kind of circle them or see them, ignore where it says pin. So probability of more than $500 is, let's start from that bankrupt. That's one that doesn't. Well, actually, here, how many are there total? There's one. Let's see what color we should use here. What'll be bright enough here that you can tell? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It would have helped to show. I think that 12 is half of them. So I think there are 24 of them. So something out of 24. Now, how many are more than 500? And are these symmetrical? Or rotationally? No. So we have to go and find which ones are more than 500. So bankrupt is not one of them. So 1, 2, 3, 4, 5. That's 500. That's not more than 500. 6, 7, 8. 550. I believe it's 8 out of 24, which is 1/3. Okay. Let's delete those. Okay, what's the probability of going bankrupt? Probability of going bankrupt is 2 out of 24, which is 1 out of 12. So these are independent events. These are independent. Therefore, the probability of greater than 500 and bankrupt, probability of greater than 500 and bankrupt is going to be the product of those two straight up. 1/3 times 1/12, and that's 1/36. You have a 1/36 chance of getting something more than 500 on the first one and then going bankrupt on the second one, of those two things occurring. Okay. All right. Oh, and I don't know if we should now, is that the first one we actually did probability, like legit for? I'll probably do a percentage of that one. So what is 1 out of 36? Because I know the examples did them. So 1 out of 36, 0.0277, etc., around 2.78%. I don't know how many decimals I should use, but that's how I'm going to round it. All right, 2.78%. Let's go. Let's go to number 12. You play a game that involves drawing two numbers from a hat. There are 25 pieces of paper numbered from 1 to 25 in the hat. Each number is replaced after it's drawn. That means if I draw it and I get an 8, I put the 8 back in there, shuffle it all up in the hat. Independent. Independent. Find the probability you will draw the 3 on your first draw and a number greater than 10 on your second draw. So this is independent. Probability of drawing a 3 is the same as probability of drawing any other number. It's 1 out of 25. You're equally likely to draw 3 as you are to draw 21 as you are to draw a 12. So it's 1 out of 25. Probability of drawing greater than 10. How many numbers are greater than 10 up to 25? 11 to 25 is 15 numbers. So that's 15 out of 25 chance, and that reduces to 3/5. So these are independent. These are independent events. Therefore, the probability of 3 and then greater than 10 is going to be 1/25 times 3/5. And that becomes 3 out of 125, which as a percentage, I know is less than 3%. 3 out of 125 is 0.24, 2.4%, thereabouts. 2.4%. Okay, number 13, problem solving. A drawer contains 12 white socks and 8 black socks. You randomly choose one sock and do not replace it. So if I choose that white socks or whatever, throw them off to the side. That set is gone. Then you randomly choose another sock. Find the probability both events A and B will occur. Event A, the first sock is white. Event B, the second sock is white. So probability of a white sock on the first one, first white sock, is going to be 12 white and 8 black. That's 12 white socks out of 8 plus 12, 20 total socks, which reduces to, divided by 4, 3/5. A lot of 3/5 coming up here. The probability of white second. This is a different set because this is going to be dependent. This is dependent because I remove this white sock. So probability of white given that white has been chosen. That's what we're doing. Now there are only 11 white socks left. I don't know if it's white, pairs of socks or socks, but 11 white socks left and 19 socks left total, or pairs of socks. And that doesn't reduce. But because it's dependent, this is now the probability. Everything's reduced by 1, probability of white given white. So now we get to still multiply these, but that's how it's going to work. So probability of white and white in a dependent case is not 3/5 times 3/5. It's 3/5 times 11/19. I would start by saying 12/20 times 11/19, and I'm probably going to go faster next time that we say it that way. Then I'll reduce it. That's 33 over 95. A little more than 33% is my best answer for now. So 33 over 95 is 34.7%. I'm just going to go one decimal place the rest of the way. 34.7%. It's a dependent event. Let's move to number 14. A word game has 100 tiles, 98 of which are letters and 2 of which are blank. The numbers of tiles of each letter are shown. So there are 9 of A, there's 1 of Q, things like that. It's like Scrabble. You randomly draw one tile, set it aside, and then randomly draw another tile. So again, the probability dependent. I'm going to first start by writing dependent. Dependent. Find the probability both events A and B will occur. Event A, the first tile is a consonant. Those are the non vowels. I'm trying to decide if Y is a vowel here. The second tile is a vowel. I'm guessing Y is not a vowel in this game. Okay, so probability of consonant and vowel. Probability of a consonant. Is this all the letters? That's 7, 14, 21, 26. Okay, all the letters are present. There are blanks. There are blanks that are present. Now, what I actually have to do here, shoot, I forgot. It's not, I don't care if it's 26. I have to add up all these numbers here. So let's do that. 9, 11, 13, 17, 31. I don't want to be wrong here, but 31, 34, 36, 45, 46, 47, 51, 53, 53, 59, 67, 69, 70, 76. I hope this adds to 100. 80. Oh, there are 100 tiles. Anyway, let's do that again. Okay, it adds to 100. First tile is a consonant. Let's take away all the ones that are vowels. I think that'll be easier. A, E, I, O, U. I'm guessing Y doesn't count. So 21, 30, 38, 42. So if there are 100 tiles, we'll take away 42, the vowels, and divide out of 100. This is probability of consonant. Okay? Now we got to multiply this by the probability that we draw a vowel given that we drew a consonant the first time because we set the tile aside. So there are still 42 vowels left in the set, but now there are only 99 tiles remaining because we just drew a tile, but we never drew a vowel the first time, so all 42 vowels still remain. So in this case, 100 minus 42, and I still have things to simplify here, but 100 minus 42 is 58, and this is 42 over 99. And I could go straight to the calculator. I want to do a little bit of fraction reduction to start. Like I could divide these by 2 and get 29 over 50, and I could divide these by at least 3, right? 14 over 33, 14 over 33, and I could even reduce 14 over 50, make that 7 over 25. So I could make it a little bit smaller like that. Ultimately, as a whole fraction, I'm getting 7 times 29 on top, which is 203. Assuming it can't reduce anymore. I don't think it can reduce anymore. 203 out of 25 times 33, which is out of 825. So 203 out of 825 rounds to, that's going to be close to a quarter, 25%. 8, a little less, 825. 24.6%. 24.6%. Now, they were dependent events, but I'll tell you what, it's not going to be much different. Given that there are 100 tiles, the independent event answer wouldn't be changing much more than that, is my guess there. Now, I want to, oh, you know what? There were 2 blank tiles. So hold on a second. If there were 2 blanks, I need to take those away from the consonants as well. It's not just consonants minus vowels. It's 44 here. So let me change everything about that. Maybe I won't do the fraction reduction one anymore. Let's just go straight to this. 56. Sorry about that. I forgot about the blanks. Now, the vowel one still remains. It's still 42. It's still 42 out of that. Maybe it would have been easier to count the other way. Those blanks, that's tricky. So 56 times 42 over 100 times 99. Let's see. It didn't change much, but it does change. So I'm not giving you the exacts, but I am going to give you the percentage. 23.75, so 23.8, 23.8% on that. Yes, the blanks. So vowels and blanks. Okay, is that all of number 14? Yes. Okay, number 15. Error analysis. Well, you should have analyzed mine that I just made a mistake on. Events A and B are independent. Describe and correct the error in finding probability of A and B. Looks like the problem is addition. So they are independent, which means you have to do something with both of those numbers there, but it's a multiplication. So they added instead of multiplied. I'm just going to say that straight up. And let's correct it. So probability of A and B is going to be 0.6 times 0.2. Now, at some point, I think it's 0.12, which is about, not about, that's 12%. At some point, we're probably going to do things regarding or, probability of this or that, and those ones become addition of things. It's not and you know, there's a reason behind that. I mean, you know, there's is. I'm just going to go ahead and say that for now. But, yeah, or would be something regarding pluses when they occur. All right, number 16, error analysis. A shelf contains 3 fashion magazines and 4 health magazines. You randomly choose one to read, set it aside, dependent, and randomly choose another for your friend to read. Describe and correct the error and finding probability both events occur. So 3 fashion and 4 health, that's 3 out of 7. Oh, first magazine's fashion, so yeah, it's 3 out of 7 for this. B given A, they said, is 4/7. Remember, probability of a health magazine in general is 4/7. But once I've chosen a fashion magazine, that's reduced my number. And I'm not going to write out sample spaces for these anymore. I'm done with that. So for number 16, let's first address the error, and then we'll correct it. So they did not treat the second probability as a true dependent set because the number of total magazines didn't decrease by 1. I wouldn't say didn't dwindle. I could have, but didn't decrease by 1. So probability of B given A, probability that you select a health magazine given that we selected a fashion magazine to begin with. There are still 4 health magazines, but now there are only 6 magazines to choose out of, which is 2/3. So it's not 4/7 anymore, it's 4/6. So the probability of A and B for this dependent event, and they're right, it is dependent, but probability of A and B in this case is 3/7, not times 4/7, but 4/6, or 2/3, and that's going to be 6 out of 21, which is about some. They wrote a decimal. I'm used to percentages now. I'm sick to that. Oh, 6 out of 21 reduces too, by the way. Let me do that. I didn't notice that I had a 3/3 here. That reduces to 2/7. So 2/7, I believe that's around 28 something percent. 2/7. 28.6. 28.6%. Okay. Okay, those are our error analysis questions. Let's keep moving forward. Number 17 on number sense. Events A and B are independent. Suppose probability of B is 0.4 and probability of A and B is 0.13. Find probability of A. Well, it's all based off this formula, right? Probability of B is 0.4. Probability of A and B. What did I do? Probability of A and B is 0.13. Given that they're independent, probability of A and B should be probability of A times probability of B. Straight up. So, probability of A and B is 0.13. You have a 13% chance of both things occurring in an independent case and a 40% chance of B occurring. So, if you multiply that by probability of A, we will divide both sides by 0.4. And that's what we're going to do here. Divide the 40% out, which makes this a number. So 0.13 divided by 0.4, I'm thinking of 13%, 13 out of 40. I didn't know that. 0.325. So 0.325. I'll go ahead and leave this one as a decimal. Everything else kind of stuck as 1 to begin with. So that makes sense. 32.5% chance of A happening. And with B, given that they're independent, there's a 13% chance of them both occurring. Number 18, also number sense. We have dependent events. Suppose probability of B given A is 0.6 and probability of A and B is 0.15. Find probability of A. So probability of B given A is 0.6. Probability of A and B is 0.15. So probability of A and B in a dependent event set means that A occurs to begin with, and then B occurs given that A had occurred to begin with, and that's how that probability changes. So we have this guy is 0.15, and then we need to find probability of A given that we have this one, B given A is 0.6. So we're going to divide both sides by 0.6. Now I know this one, 0.15 by 0.6 should be exactly 1/4. So that's 0.25. Okay, number 19 and 20 on analyzing relationships. You randomly select 3 cards from a standard deck of 52 playing cards. What's the probability all 3 cards are face cards when you replace each card before selecting and you do not replace each selecting the next card? Now, the first thing we're going to have to know is probability of selecting a face card. Probability of face, there's the Jack, Queen, King of all suits. So 4 suits, 3 cards per suit that are face cards. That's 12 out of 52. Probability of a face card is 12 out of 52 to begin with. Now, that reduces, for my sake, I'm going to kind of refer to that. I'll refer to that after. But it reduces because you can divide them at least by 2. I think by 4 as well. So probability of face and face and face when you replace each card. So 3 face is when you replace them, that means they go back. That means probability is equal each time. So it's whatever this number is cubed. When you divide this by 4, you get 3 out of 13. And that makes sense. There are 3 face cards per suit and 13 cards per suit. So 3 out of 13 cubed is the way that I'll say that one. I don't know what 13 cubed is. 13 cubed is 2197. So it's exactly 27 over 2197. That can't reduce, but let's go ahead and get that percentage. 0.012, so about 1.2% odds, not odds, probability that will occur, which is low. That's low. Was that part A? Did they say as A? I know they said the things. Yeah, A and B. You do not replace each card. So probability, so the first one was independent. The next one is dependent because this time you do not replace the cards. That means that when I draw a face card, it changes the probability of drawing face cards afterward, whether or not you were drawing a face card. But it starts by 12 out of 52, and then a face card is removed, and a whole card is removed, so 11 out of 51, and then it goes down to 10 out of 50. So this keeps reducing each time. Now, if I'm trying to get an exact answer reduced, 12 out of 52 we knew was 3/13. 11 out of 51 I doubt reduces, so I'll leave it like that for now, but 3 and 51 can reduce, I'll get to that. And 10/50 is also 1/5. So 3 out of 51, because 17 times 3 is 51, so that's 1/17. 1/17. Now on top, I just have 1 times 11 times 1, which is 11. And on the bottom, I have 13 times 17 times 5, which I don't know what that is. I know 13 times 5 is 65, but I get my calculator. 13 times 17 times 5. So an exact fraction is 11 out of 1105. That's really close to 1%, y'all. I don't know how close that is, but really close. When it comes to rounding, it's 0.0099. I'm going to call that about 1.0%. 1.0%. So it's slightly lesser chance. How many times lesser are they asking? Yes, they are. Compare the probabilities. So we got to divide this percentage by this percentage. But remember, those are rounded numbers. So when it comes to comparison, if that's part C, they don't really say part C, but I want to call it that. Let's do 27 over 2197 divided by 11 over 1105. Now, that's good that I wrote those numbers out because they're smaller versions of what I had. And remember, if you're doing this in a calculator, let me show you my calculator now with this. When I do this in a calculator, I don't require parentheses out of the first one, but I do require parentheses out of the second one. I got to take this divided by, and here I do 11 over 1105. Now, there are other ways you can do this by hand in other cases. So 1.2345, that's weird. About 1.23 times bigger. Percent times bigger, I'll just say. So anyway, there are other ways that I can do that in here as well, because division by a fraction is also multiplying by the reciprocal. So I could have also done this times this. And who knows, maybe something can reduce among these two. I have no idea. But I'm just going to go off of it like that. So about 1.23 times bigger when it comes to the rounding that I chose to state. Okay. Anyway, let's go to what number was this? 19? Let's go to number 20. A bag contains 9 red marbles, 4 blue marbles, and 7 yellow marbles. You randomly select 3 marbles from the bag. What's the probability all 3 marbles are red when you replace them, and versus when you do not replace them? So, same kind of idea. I mean, these are pretty close to what we were doing, obviously, in the example sets if you saw the lecture portion. So, probability of red to begin with, there are 9 red marbles out of a total of 9 plus 4 plus 7, that's 20 total marbles. That cannot reduce, so we'll leave it like that. So for part A, probability of 3 red in an independent setting. Independent setting is 9 out of 20. Times 9 out of 20 times 9 out of 20. Which is 729 out of 8,000. Which is about 9.1%. Now I'm going to keep that exact answer that I had before, so about 9.1%. Now part B, you do not replace each marble. So 9.1% to start. Part B, 3 red in an independent case, or excuse me, in a dependent case, My handwriting is not good tonight. I'm very sorry about that. Let me try harder. So 9/20 times, I just chose a red. Now there are 8 red and 19 marbles left, times, now there's 7 red and 18 marbles left in that case. So again, I want to try and reduce this if possible. There's no requirement for that, but I think it helps myself with sanity. 9 over 18 is 1/2. 8 divided by 2 is 4 over 1, and 4/20 is 1/5. So now I have 7 on top, and 5 times 19 times 1 on bottom. 5 times 19 is 95. So 7 over 95 is the way that I'm writing that, and I prefer that appearance. So 7 over 95. If I trust I did that right, 7.36, so about 7.4%. 7.4% probability there. And I'm trusting the answer. It is lesser than that, and it should be because the number of red had diminished over that time, and they are going to compare them. Compare the probabilities. We're going to do one divided by the other. This time, let's write it as I was saying before. Let's do 729 over 8,000 times, and then let's flip that, 95 over 7. And 729 can't divide by 7 as far as I can tell, but 95 over 8,000 can reduce to, you can at least divide by 5. I'm sure that's it. But it can reduce to 19 over 1,600. So it can reduce this to 729 times 19 over 1,600 times 7. And I know that's probably unorthodox to really care about there, but let's just do that anyway. So let's do 729 times 19 over 1,600 times 7. Anyway, I was just stating the things that you can do when it comes to overall fraction reduction practices. I don't think that really matters for this problem. And I get that 1.23 number again. It's a different one. It's 1.2366, whatever. So it's about I'll say 24, about 1.24% there. So very close. Oh, not 1.24%. 1.24 times bigger. Times bigger. So very close to the previous answer that we just had. 1.23 on one, 1.24 on the other. Okay, let's go to number 21. Attend to precision. 10 more questions. The table shows the number of species. How long have we gone? Hour 12? Hopefully they speed up. Here's the two-way table things. The table shows the number of species in the United States listed as endangered and threatened. Find the probability a randomly selected endangered species is a bird and the probability a randomly selected mammal is endangered. So these are conditional probabilities, and one thing I'd love to do on these, I don't know if it's a overall recommended kind of thing, but I'd love to tabulate totals of these things because they tend to kind of be used. So as far as totals here, I want to find totals of each part because those are the ones we're going to be dividing out of as a general sense. Most two-way tables actually have those, and I'm sure we're going to have those later. They're known as, are they known as joint frequencies, I believe? Joint frequencies? Like 70 plus 16 is 86, 80 plus 16 is 96, 318 plus 142 is 460, and then 70 plus 80, 150 plus 318 is 468, 16 plus 16, 32 is 142 is 174, and this plus this plus this should be the same as this plus that, and I don't want to mess up that number, and I want to make sure they're both right, so I'll do that fast. So 468 plus 174, and I don't think I need that overall number. I'm just making sure I did the other ones right. I got 642, so 86 plus 96 plus 460 is also 642. Okay, so I'm just putting these out there so we can talk about why I'm getting the numbers that I'm getting later without needing to show extra work on it. So let's go ahead and take a look at that question again. What was it? Part A, probability a randomly selected endangered species is a bird. Notice the conditional aspect of this. We're finding the probability that we are getting a bird given that it's endangered. We're only looking at the endangered set for this. So, among the endangered, among the 468 that are endangered, how many of those are birds? I don't care about the 96 birds because I don't want to count the threatened ones. I don't care about the 642 total population. I care about the 468. So this is going to be the probability of being birds and endangered divided by the probability of being endangered. So we're doing 80 over 468. I'm not going to worry about fraction reduction this time. I'm going to get straight into percentage. So this will be 17%, about 17.1%, 17.1% probability of birds given that they are endangered. I know they didn't specifically say given that they are endangered. They never said conditional probability, but they said a randomly selected endangered. So they're telling you what it is that we need to know out of that. Next question. Part B, probability a randomly selected mammal is endangered. This time we're looking at the mammals. So notice that, a randomly selected mammal. It's like a randomly selected Californian is in Los Angeles, right? This is what I was talking about before. So there are 86 mammals. Among the 86 mammals, how many are endangered? Probability of endangered given mammal is going to be probability of endangered and mammal, 70 out of the 86 total mammals. So 70 out of 86, again, can reduce, but let's straight calculate it. 70 over 86, about 81.4% of those ones. So they are conditional probabilities. That's how we displayed that. So I think I'm just going to make sure to kind of do that each time here on out. All right, maybe I won't write the totals this time, but I'll go ahead and add them up when I need to for number 22 because it seems like the same kind of problem like number 21. All right, number 22. The table shows the number of tropical cyclones that formed during the hurricane seasons over a 12-year period. Find the probability to predict whether a future tropical cyclone in the northern hemisphere is a hurricane, and probability to predict whether a hurricane is in the southern hemisphere. So let's look at how that conditional aspect is working this time. Again, they don't tell you it's conditional, but what they say represents conditionality. Probability to predict whether a future tropical cyclone is a hurricane. So, type of tropical cyclone. In the northern hemisphere. So, we're looking at all the cyclones. I was like, they're all cyclones. So, among the northern hemisphere sets, because that's what they say, right? Whether a future tropical cyclone in the northern hemisphere. So among the 100 plus 342 plus 379, how many of them are hurricanes? That's what they're asking. So probability of hurricane given northern hemisphere. So we're going to take 379 and divide that by the total of those 100, 342, and 379. And I would have done the same thing I did last time, but because we're only doing it for like a single question, I think here we might as well just do it like that. So I'm going to calculate this straight up right now. 379 divided by 100 plus 342. And I'm doing this in parentheses, by the way. 342 plus 379. 0.4616, so about 46.1% or 46.2%. 46.2%. 379 out of whatever total that was. There it is. Part B. Probability to predict whether a hurricane is in the southern hemisphere. So among all hurricanes, among the 379 plus 529 hurricanes, how many are southern hemisphere hurricanes? So probability of southern hemisphere given hurricane is going to be 525 out of the sum of 379 plus 525. Which is that 904, 525 or 904. I don't know. If you calculated that, I think that's what you get. 525 over the total, 379. It's probably worth to add those up to begin with anyway, so you don't mess it up in your calculator. But I'm giving you the math. You can kind of figure it out from there. About 58.1% for that one. So 46.2% for the first, 58.1% for the second. All right, number 23. Number 23. At a school, 43% of students attend the homecoming football game. Only 23% of students go to the game and the homecoming dance. What is the probability a student who attends the football game also attends the dance? So 43% of students, so probability of homecoming, so probability you attend homecoming is 43%. 23% of students who go to the game go to the game and the homecoming dance. So probability of, I guess I'll abbreviate these, homecoming and dance is 23%. What's the probability that a student who attends the football game also attends the dance. We need the probability that you attended the dance given that you attended the homecoming game. Okay, so the scenario here is you got to take the probability of all that attended both and then divide by, so we're doing one divided by the other. We're going to do 0.23 divided by 0.43. 0.23, or 23% divided by 43%, but 0.23 divided by 0.43 in that scenario. I'll explain why in a moment, but 0.23 divided by 0.43. So that's 53.5% about. 53.5%. Okay, so here's the idea. They say probability of a student who attends the football game also attends the dance. We only care about the ones that attended the football game. Who cares about the other 57% who didn't? We don't care if those people went to the dance or not. These people did, and within that pie chart, 23% of them also went to the dance. Sorry, 23% of all students went to both the homecoming game and the dance. So within that set of those who went to both, divided by the ones who just went to, or who did go to the homecoming football game, and we get that. So 53.5%. That's the conditional probability formula, though. Probability of B given A is probability of A and B divided by probability of A, or whatever, whichever way we say it. Number 24. At a gas station, 84% of customers buy gasoline, only 5% of customers buy gasoline and a beverage. What's the probability of a customer who buys gasoline also buys a beverage? So it's the same kind of question as before, only it's, this one. At a gas station, 84% of customers buy gasoline. I'll put probability of gasoline purchase is 84%. I'm going to write it as decimals. 0.84. I said I would write better, and I didn't. 0.84. Probability of gasoline and beverage by gasoline and beverage is 0.05. That's 5%. A customer who buys gasoline also buys a beverage. If you buying a beverage, given that you buy gasoline, so we have to look at the entire gasoline crowd only, divide it only by them, and let's look at all of those who bought gasoline also buy beverage. 5% over 84%. You can literally just do 5 out of 84 on your calculator, but I'm using the percentage version to write that. So 0.0595, so that's around 5.95%, around 6.0%. 6.0% of those who bought gasoline also bought a beverage. Okay, let's move on to number 25. You and 19 other students volunteer to present the Best Teacher Award, Mr. Robinson, at a school banquet. One student volunteer will be chosen to present the award. Each student worked at least 1 hour in preparation for the banquet. This is an interesting question. You worked for 4 hours, and the group worked a combined total of 45 hours. For each situation, describe a process that gives you a fair chance to be chosen. Find the probability you are chosen. So I think the idea behind the fairness is like, hey, if I worked like half the time, then I deserve a 50% chance of going up there. Or, hey, I did all the work, so I should go up there. Kind of like that. So your 4 hours, you did 4 hours. Hey, I get a 4/45 chance that I should go up there. Kind of like that is kind of the thought process to me here. So fair. Oh, sorry. They have two different ways to say fair. That's part B. So what I just said, I think, is part B. Anyway, I did not read that at all. I thought I was supposed to come up with my own strategy. I'm sorry. So part A, fair means equally likely. So for each situation, describe a process that gives you a fair chance to be chosen. Find the probability you're chosen. So fair means equally likely. You and 19 other students, each person gets there are 20 students. So each student gets a 1/20th probability of being chosen. I thought we were going to do a whole dependent-independent thing on this thing. I guess not. So that's part A. Everyone gets 1/20th. Now 1/20th is also 5%. Excuse me. 1/20th is also 5%. So that's just kind of how that would work in that scenario. Do they want the actual process, though? I thought they were just saying the form. Okay, so process-wise, I would say use a calculator. Place names in a hat. Yeah. What else is out of 20? Yeah, place names in a hat. Place names in a hat. And randomly draw. Placed each name in a hat once. Each name in a hat once. Because that gives equal likelihood. So all 20 names. Now part B, the idea here is that, and I forget how it said it for you. What did it say? You worked for 4 hours and the group worked a combined total of 45. So for yourself, each student worked at least 1 hour in preparation. I don't know how the others will be put in, but you worked 4 of them. So if you do the hat thing, well, first of all, you get a 4/45 chance. You get a 4/45 chance of being selected. Whereas other students, what would be fair for them? They said worked at least 1 hour. I don't know if that means somebody could have worked 20. Well, no, I guess that's not possible. But each worked 1 hour because 4 out of 45. I would just say, I don't know what I would say for that. Because it's you and 19 other students. For 19 other students, if their name is all put in once, then that's a total, like the thing I was going to say is if we put names in a hat, you can put yourself in 4 times. But for each of the 19 other students, if all of them put their names in once, now that's 23 out of... I'm just trying to think for the other students' case what we would do in this situation because I don't really have that idea. Let's see. I would say that... I don't know if they're talking about you specifically. I would just say that we put our names in with equal weight to the number of things that we had because it did say proportional. So put each student in based on the number of hours they worked. How about just that? Based on the number of hours that they worked. There we go. Okay. Do we have to... find the probability you're chosen. I didn't even see that. So probability that you're chosen in each of these situations. So probability of me here is 1 out of 20. That's 5%. Right? 1 out of 20 is 5%. Probability of me in this case is 4 out of 45, I believe. That's how I was saying it before. So 4 out of 45 is 8.9%. It's 0.8 repeating, but 8.9%. Larger percentage because it's fairer because you worked more than other people. All right, 5 more questions. Number 26, how do you see it? A bag contains 1 red marble and 1 blue marble. The diagrams show the possible outcomes of randomly choosing 2 marbles using different methods. For each method, determine whether the marbles were selected with or without replacement. So in part A, and they don't say explain, so I'm not going to type it, but I'll explain. In part A, your first draw is red, second draw is blue, and here first draw is blue, second draw is red. Whereas here you see when you select red, then you can either get red or blue, and blue you can either get red or blue. So part A is a without replacement set, that there's only 1 red and there's 1 blue. So without replacement. And then part B, I'll format this. Hold on. Replacement. The first one's without replacement because your only option is to select blue once you selected red. That's a dependent case, of course. Here, if I select red and I put it back in, then I can still select that red again, possibly. So that's the without and that's with. Remember, without means dependent. And with replacement means independent, at least in large part, that your outcome now either changes or doesn't change. Your probability changes or doesn't change depending on the first outcome. All right, number 27, making an argument. A meteorologist claims there's a 70% chance of rain When it rains, there's a 75% chance your softball game will be rescheduled. Your friend believes the game is more likely to be rescheduled than played. Is your friend correct? Explain your reasoning. Okay. The rescheduling is based, it's the 75%, it's not 75% chance likely to be rescheduled, it's only if it rains that happens. So there's a dependency to it, but that part is already factored into the percentages. If there's a 70% chance rain, what we're trying to find is probability of rain and rescheduling. So it's a dependent event in that your probability of being rescheduled is based on the fact it's probability that it's going to rain, but that's already factored into this. So 70% chance, we're going to multiply these. We're going to take the probability of rain, 70%, and multiply the probability of rescheduling given that it rained. That's the 75%. We're going to multiply those two. Now, when you multiply those two, you get a value. What is 0.7? What's 70% of 75%, right? That's what there is, 75% of 70%. It's 52.5, 0.525 or 52, not pout. It's exactly 52.5%. Your friend believes the game is more likely to be rescheduled than played. That is true. As long as it's more than 50%, your friend is correct. Let me type this. Your friend is correct. Because the probability of rain and rescheduling is more than 50%. So the reason I calculated that would be just the way that the conditional probability thing works. So yes, because it's more than that thing, that it would do it. Number 28. 2 6-sided dice are rolled once. Events A and B are represented by the diagram. Describe each event. Are the two events dependent or independent? Justify your reasoning. What events? They just call them A and B. I didn't look at the diagram yet. I thought I was going to look for event A and event B. Event A. Okay, so they have numbers here. What do they say? 2 6-sided dice are rolled once. So let's say that you rolled a dice here and you landed on something, and then you rolled a second. Actually, let's start with this, X then Y, right? You rolled a dice, landed on one of these numbers, and then you rolled it. So it's like if I rolled a 3 first and then a 1 first, then that's this dot, which apparently is not event A or B. So what does event A represent? Event A represents either... Event A represents getting a 2. Rolling and landing on a 2. Notice that the column here and the row here are only representing 2s. That doesn't mean you got 2 2s, because I could get a 6 and then a 2, or I could get a 2 and then a 5, something like that. So they said describe each event. So event A represents landing on a 2 on either roll. That also means you can do 2 2s. Sometimes there's something called exclusive OR cases, like a 2 or a 2, where if you get 2 2s, it doesn't count for the scenario. This one is fine. Event B, I didn't look at event B yet. Event B has either a 4 and a 1 or a 3 and a 2 or 2. Okay, so numbers that add to 5. So event B represents a roll sum of 5. What do they want us to do with this? Are they dependent or independent? So when you're talking about the case of A and B occurring, remember, this is just 2 dice rolls. Event A can affect event B, because if you land on a certain thing for A, if you land on a certain dice roll, wait, are the events the... I have to think about it in a description sense. I can do it mathematically, but I have to think about it in description sense how I'd want to say that, because I'm thinking more of the dice rolls than the event occurring, because the event occurring is the thing after 2 dice rolls. Anyway, I can't think of the way to say it out loud with it, but let's do the math version of it. What's the probability of event A occurring? The probability of event A occurring is 1, 2, 3, 4, 5, 6, and 1. Remember, there's an overlap on that twos, so there are 11 of them out of 36 possibilities. That's the probability of event A. Probability of event B, there's only 4 out of 36, which, by the way, reduces to 1/9. We have to see, and the probability of A and B, probability of A and B occurring, we have to find the overlap of those. I think it's just these two. That's the only overlap where there's both A and B that occurs, and that is 2 out of 36 or 1 out of 18. We have to see if does 11 out of 36 times 1/9, does this equal 1 out of 18, or 1 over 18? And that's, I don't know what 36, well, let's see, that's 324. So 11 over 324, which I doubt reduces, but I'm just going to compare them anyway. I'm going to assume no. 18, 1 out of 18 is actually, I think, 18 out of 324. So these are not independent. These are dependent events. Dependence. That's not the first time I wrote that. They are dependent events because the multiplication of one set does not equal the and for the other in that case. Okay. Anyway, so there's that one. Yeah, I'm trying to think of the explanation of the outcome, the probability of one occurring is affected by the outcome of another. See, I consider the trials to be the dice rolls, not the event of one occurring. I don't know how to state that in that way. It's a weird case of dependency that I don't know if I can state logically. All right, number 29. A football team is losing by 14 points near the end of a game. The team scores 2 touchdowns worth 6 points each before the end of a game. After each touchdown, the coach must decide whether to go for 1 point with a kick, which is successful 99% of the time. Not true anymore with the extra point thing back, but that's okay. Or 2 point, well, that's fine. I'm going off their numbers. Or 2 points with a runner pass, which is successful 45% of the time. I like where they're going with this. I like this idea of these things. I don't know if these are actual true numbers back when, but this is good. If the team goes for 1 point after each touchdown, what's the probability that the team wins, loses, ties? Assuming they're not talking about, okay, because it says ties. So assuming there's not overtime. Part A, probability of a win. They're down by 14. Wait, if the team goes for 1 point after each touchdown, let's see. The team scores 2 touchdowns before the end of the game. So they only score 2 more touchdowns. They get their 6 points there, and they have a 99% chance of kicking a field goal, getting the extra point on those ones if they go for the 1 point after each touchdown. Here's the thing, though. You can't win. You can only get those. It can end in a tie, apparently. Most you can get is 14 points, which would only tie it. Probability of win is 0%. There's no such outcome you can get that one. So let's take that one away. Probability of a loss, I'll tell you what. Let's start with the probability of a tie. Because probability of a tie is what's going to happen if you make both of them. So what you got to do is take the 99% chance that you score the first field goal, that you make the first field goal, times the 99% chance you make the next field goal. Remember, they're independent events. Making the first one doesn't change the probability that you make the second one. So 0.99 squared, which of course I know at the top of my head, yes, without me clicking on my mouse here, is 0.9801. Let's go ahead and write that as the exact 98.01%. Now, the reason I did this one first is because we know the probability of that one here. I can do the opposite of this to say probability of loss. You either do one of 3 things here. You win, lose, or tie in this scenario. So in this scenario, well, actually, no, I take it back. There are the other things you can do here. You can make, I don't know if I said that one out loud right, but probability of a loss. Oh, wait, there are different ways. Okay, yes, okay, you either win, lose, or tie. Anyway, so with that here's what you don't want to do. You don't want to do probability of missing the first and probability of missing the second, because you can just miss one of them and lose. That's why there are 3 different cases here. You can either miss both of them, or miss the first and make the second, or make the first and miss the second. And all three together add to the percentage that's not 98.01 plus 0%. So you got to take the 100% minus 98.01. I know we did that once last, and that'll get you what? 1.99% probability of loss. So that one's a little bit trickier because you have to do the sum of all those other cases that can occur there, right? But that's three different things. There's a, let's see. I'm trying to say, I don't want to say make and miss because those will start with M. Score versus miss. You can either score the first, miss the second, miss the first, score the second, or miss both. And if we added all three probabilities up, you'd get 1.99%. You don't just want to do 0.01 times 0.01. All right, is that it? Oh, that's just part A. Part B. If the team goes for 2 points after each touchdown, what's the probability the team wins, loses, or ties? So now that they go for 2, it's the same concept as before. Probability of a win, if you get both of them, you will win. Now, that being said, they're going for 2 on both cases. So you get a 45% chance the first time and a 45% chance the second time. So in that case, isn't that 20 point? I think 45 squared is 2025, but 0.45 squared. Yes. So I actually knew that one. 20.25%. 20.25%. That's probability of win. Probability of a loss, once again, well, probability of a loss, you'd have to get, I will do this 1 second, you have to miss both. Because if you make the tie would occur if you make the first, convert the first extra point, or convert the second extra point. Not both, where the win occurs. But if you miss both extra points here, 2-point conversions, if you fail, that's 1 minus 0.45 times 1 minus 0.45. Or 0.55 times 0.55. You must miss both. Miss first and miss second. I don't remember 0.55 squared. Was it 3125? No, 3025. 30.25% probability of losing. So probability of tie will be everything else. Now remember, that's either converting first, not converting second, or not converting first, converting second added together. It's an OR case. And we haven't talked about OR cases, so we really just got to do the 100 minus all these ones, because there's a 100% chance that one of these three things happen, and you have to account for all of them. So this plus that plus 30.25. So that'll be 100 minus 50.5, which I guess is 49.5% chance. So 49.5% chance of that one. All right, part C. Can you develop a strategy? Ooh, I like this. So the coach's team has a probability of winning the game that is greater than probability of losing. If so, explain your strategy and calculate the probabilities of winning and losing the game. I'm guessing it's the one where you try and kick a field goal and then you try and then do the 2-point conversion. Something like that. It's probably a combination of both, because winning here was 0% chance. Winning here was 20.25% chance. So we have to see if something else works here. So develop a strategy. Let's try the whole kicking a field goal and then doing the 2-point conversion thing. So I'm going to write as a question first. If you kick a field goal, if you kick an extra point and then make the 2-point conversion, let's see if that works out. In order to do that, and I'm not going to call it probability of win. I just want to see the probability of field goal and 2-point conversion. So that's a 99% chance of making the first, and then 45% chance of making the second. That doesn't sound like more than 100%, but you can do that in more than one way. You could also do the 2-point conversion first and the field goal second as well. So I think you do get to add those ones up. I shouldn't say and then. I should say either or. And in real football, I gotta admit, these wouldn't be these wouldn't be independent events in real football. Because in real football, it's likely you'd want to go for the 2-point conversion first. Oh. There are other options here. Hold on a second. Ooh, hold on. Let me change even how I said this. Here's the thing. If you do the 2-point conversion first and you're successful, so there is a dependency here. If you do a 2-point conversion first and you're successful, then you can either decide to do the 2-point conversion next after or the field goal. And I think that maximizes it. So actually the and then would work. If you convert a 2-point conversion first, then you can win in one of two ways. Either with the field goal, extra point, or 2-point conversion. Now, would you prefer doing that 2-point conversion thing? Not necessarily, but given all the different outcomes, see, this goes back to that sample space thing. When it goes to all different outcomes of what you can do, you want to see which ones give you a win. So I almost feel like doing a tree diagram here and saying what you can do to win versus lose. Let's take a look at this. All of these have different percentages. So if you kick, okay, I'll call this field goal versus 2. Sorry about that. Field goal versus 2. A field goal, 99% chance of happening. 2-point conversion, 45% chance of happening. From there, you can either kick another field goal, which is another 99%, or do the 2-point conversion, which is another 0.45%, or here, you can either do the field goal or 2-point conversion, another 0.99 or another 0.45. Now, there are cases of misses as well that I think I'm supposed to be doing in these tree diagrams, because this doesn't add up to all 100%. Shoot, maybe the tree diagram is not a good idea, because you either make, miss, like that kind of thing. My point with it is this. There are certain ways that you can lose the game. Okay. Maybe I should just spell them out and not do the tree diagram. I'll just say all the different ways you can lose the game. Ways to win. Ways to tie. Ways to lose. Ways to lose. So here are the ways you can win. You can either do 2-point conversions, a 2-point conversion and a field goal, or a field goal and a 2-point conversion. Ways to tie. You can either do 2 field goals, 2 extra points, a 2-point conversion and miss a field goal. See, that's how I'll say it. Or a miss field goal and a 2-point conversion. Ways to lose. Everything else. Now, everything else includes what? 2 misses, fails on 2-point conversions. Oh, I'm sorry. These aren't just missed field goals, huh? You can do 2-point conversion and a missed 2-point conversion, and this as well. But this is 2 misses, failed both 2-point conversions, failed a 2-point conversion, missed a field goal, failed a field goal and 2-point conversion, or missed a field goal, failed a 2-point conversion. Made a field goal, missed a field goal, missed a field goal, made a field goal. Failed a 2-point conversion, made a field goal, failed a 2-point conversion. I might have missed some things along the way. This is where it gets a little bit weird with that. If I make a 2-point conversion, I don't lose. I at least tie. So I just got to make sure that I either miss, don't convert, or only make a single field goal and look at all those different opportunities. And I think that's all of them. So what are the ways to win? These ones here. But notice that if I kick a field goal first, I'm taking out, first of all, that's less opportunity to win because I have 2 other ways to win here if I get the 2-point conversion first. And making a field goal gives me possible ways I might be tying or still losing. So the best way to do this is to get the 2-point conversion first. Now, there are the 2 different ways to do it. You can either get 2 2-point conversions or 2-point conversion field goal. So probability of win in this case is you take your 2-point conversion times another 2-point conversion probability plus your 2-point conversion times probability of field goal. Those two together, this or that, will give you all the different ways that you can win. I don't know if that's more than 50%. I assume that it is. So this is what people would strategically do. This is what teams would strategically do here. So 0.45 times 0.45 is 20.25. We did that. Plus 0.45 times 0.99. That is, yes, 64.8%. That's 64.8%. So that one increases your probability by going for the 2-point conversion first. You're like, well, what if you fail? That's factored into the probability. That you only have a 45% chance of being successful. This is factored into the probability. You're much more successful in doing it this way. Now, if you make the first one, you should be kicking the field goal, but this is also another option. This is a part of the overall 100% chance of something that can happen. So it gets included in the ways that you can win. And that's how I believe that this one should be working itself out for that one. Okay. Anyway, so I don't know if that's for sure right with that, but that's the idea there as far as ways to win. I want to go off of those ones. I feel like I might be missing something with that, but that feels like that's good. Is there overlap with that? That kind of feels like high probability of success suddenly. I got to think if there's overlap with that because the fact that I did those two there. What's the question? Oh, it just says, it doesn't say probability of winning the game. It says probability of winning greater than probability of losing. All right, I'm not doing too well on this problem. I want to let you know that. This is me talking through and trying to figure these things out. So those are ways to win and such. But you want to just beat the probability of losing in each case. So I'll say I'm struggling on this one. I'll say it's a cool problem. I'll say this is why they pay other guys the big bucks to do these things for football. Because here's the thing. If I'm unsuccessful on my 2-point try, kicking a field goal means I will lose, right? Because I only get 13 points total, not 14. I can still go for that 2-point conversion and still tie, and that's still not a loss. And the probability of winning would still be higher. Okay, I don't know if I can get your numbers for you. For the sake of time, I will move on. I feel like this is something I can do in another video later if I really get a good handle of what it is I'm talking about, because I'm going beyond what I feel I should on this problem. So I want to think of that one more. I want to definitely have that conversational piece at a later time. Apologies for that one. Not the best thing I can think of for strategy stuff. That one kind of came on the fly. I read it wrong, and I don't want to go beyond that, especially when I was going to do a tree diagram, stuff like that. All right, let's move forward. Let's do the last question. I will do another video on that, a follow-up one for you guys later. Number 30, abstract reasoning. Assume that A and B are independent events. Part A, explain why probability of B equals probability of B given A, and probability of A equals probability of A given B. Well, assuming that they're independent events, probability of B given A means the probability of B. Oh, well, they're saying that. A occurring doesn't change B's outcome. So probability of B given A, let me type this. Probability of B given A means probability that B occurs given that A occurs. But if they're independent, then A occurring does not change, does not alter B's probability of occurring. Therefore, probability of B equals probability of B given A. Because no matter whether A occurs or not, probability of B still has equal likelihood of occurring the way that it did before. Exact same thing for the other one. I mean, if I'm just going to copy paste and change the letters A and B around if they actually want me to do that. But it's like vice versa. Same goes the other way. I'm not even going to read out loud what it says. You can read it afterward, but it's literally just the opposite. There you go. Did I change them all? Yes, I think I did. All right, that's part A. Part B. Part B, can probability of A and B also be defined as probability of B times probability of A given B? Justify your reasoning. Well, what we do know is that the probability of, oh, this is assuming they're independent. I see what they're saying. Probability of A and B. We know that in an independent case, that means probability of A times probability of B. Well, now that we know, let's see, they use a B here. Now that we know that probability of A can be written as probability of A given B, let's take that and substitute it in for probability of A. So now it says probability of A given B, and we're trying to make it look like what? Hold on. P of A and B. That's a substitution of that. What do they want to say? Probability of B. Yeah, so yes, we can. So I'm just going to rewrite the order in which they're written. Probability of A given B, let's write this one first. Probability of B, I don't know why I'm in blue now, times probability of A given B. Yes, we can. That's a substitution. That's my justification for it. So yes, we can, and that's it. Okay, guys. That ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. So here's the thing. I don't know how I'm going to decide to do an edit or decision thing with this video, but number 29, part C, I feel like I did not fully complete because they were asking about strategies for the football game scenario of winning being greater than losing. I didn't read the greater than losing part, and I started to go down a rabbit hole of doing more explanation than doing the problem, and I feel like I can do it more justice in a separate video. At some point, I'll look to do it. It's not going to be in its immediacy like right now. I'll be honest, I'm recording this right now. It's 12:15 in the morning, and I have school tomorrow. I got to teach tomorrow. So I'm not doing it in this portion of this video. That's why I kind of refrained, and I said I didn't really attack it right, and I was kind of going on a different tangent. I'll look at it later when I have a clearer head on what I want to say about it, answering the right question being asked. So whether or not I chopped that part out of this video or not, I don't know yet because I'm just saying this right now. You'll tell by the edit. If I follow up on it, it'll be its own separate video, a companion video of sorts. I've done that before for a frustum problem. Yeah, so I'll do it for you there as well. So guys, that'll do it for this one. This is Mr. Robinson. Take care. I will see you in the next one.